And our speaker today is Enrique Macias-Virgo from the University of Santiago de Compostela, and he will talk about homotopic distance and generalized motion planning. Kike, take it away and share your screen, please.
Thank you. Okay, thank you very much to the organizers for inviting me to give this talk. As John said, I will speak about the homotopic distance and generalized motion planning. This is a joint work with David Mosquera and Maria Jose Pereira, and I shall explain how Lusternik-Schnirelmann category and Farber's topological complexity are particular cases of a more general notion that we call homotopic distance between maps. First, I shall recall the main properties of the homotopic distance, and second, I shall show that if you have a manifold where it is defined a Morse-Bott function, then the homotopic distance between two maps is bounded by the sum of their subspace distances on the critical levels. This generalizes both the Lusternik-Schnirelmann theorem, at least for Morse functions, and a similar result by Farber for the topological complexity. And as an application, I shall show how navigation functions can be used to solve a generalized motion planning problem. So everybody knows the definition of homotopic maps, but imagine you have two maps which are not homotopic. Then you can define the homotopic distance as the least integer number k, such that there is an open covering of X by k plus 1 open sets, such that F and G are homotopic on each UI. This is the definition of homotopic distance. Of course, two maps are homotopic if their distance is 0. I shall use this notation, which is very useful in the proofs and was suggested to us by a referee. If you have a covering, I shall denote uppercase bold U, the disjoint union of the open sets, and lowercase bold u, the map induced by the inclusions, in such a way that if the maps F and G are not homotopic, their compositions with bold u are homotopic. This simplifies many proofs. So the first properties of the homotopic distance are obvious. The first one, it is symmetric. The distance between F and G is the same as the distance between G and F. The homotopic distance only depends on the homotopy class. If F and F prime are homotopic and G prime are homotopic, then the distance doesn't change. And finally, by definition, the distance is 0 if and only if the homotopy classes are equal. So, in fact, the homotopic distance is a homotopy invariant of the pair. That means if you have two pairs of maps connected by homotopy equivalencies, like in this diagram, then the distance between F and G is the same as the distance between F prime and G prime. One can try to prove the triangle inequality, but in general, it is not true. We have a counterexample in finite topological spaces, but it is true if the domain X is a normal space. And for that, for the proof, we use a nice lemma by John O'Prey and Jeff Strom that says that if you have a normal space with two open covers U with n plus 1 elements and V with n plus 1 elements, such that each set of U satisfies some property A and each set of B satisfies some property B, and you assume that properties A and B are inherited by open subsets and disjoint unions, then there is a third cover of size n plus 1, which satisfies both property A and property B. So this is a nice result if you take as open sets the open sets where F and G are homotopic and the open sets where G and H are homotopic, then you will find a covering where F and G are homotopic and you will have the triangle inequality. As we shall see, many properties of the homotopic distance come from its behavior under compositions. If you have two maps and you compose them on the left by another map H, then the distance of the composition is less than or equal to the distance between F and G. And the same is true if you compose on the right. This result will be very useful in many proofs too. So the first easy computations show that, for instance, if you have two maps defined on R, then the distance is 0 because R is contractible. On the sphere S2, if you have the identity and the antipodal map, then the distance is 1. On the group of unitary complex numbers S1, if you have the identity and the constant map, then the distance is 1. And on the group U2 of 2 times 2 unitary complex matrices, the distance between the identity and the inversion map is 2. So clearly, the distance is related to the number of contractible open sets that you need to cover the domain. So now I will speak about Lusternik-Schnirelmann category. You know the definition, the LS category of a topological space X is the less integer number K such that there is an open covering by K plus 1 open sets, and each one is contractible in X. So it's clear that at least if X is path connected, the category is just the distance between the identity and any constant map. This is a typical example of a sphere which has category 1. And there is another proof, another result, which says that if you take a base point x0 and we take the axis inclusions I1, I2, then the distance between I1 and I2 is the category. And the proof is very easy if you use the notations and the results we had before, because the open covering satisfies this. And then you just write the map I1 as this map, and you use the homotopies, and you find the result. So proofs are very, very easy. In general, the relationship between the distance and the category is that if you have two continuous maps and the domain and the codomain are connected, path connected, then the distance is less than or equal to the category of the domain. And again, the proof that you see there is very easy. Just you write with the notation we said, and you use that two constant maps are homotopic. So now we shall relate the distance with the topological complexity. By definition, the topological complexity of the space X equals the distance between the two projections P1 and P2. This is not the original definition, but it is easily seen to be equivalent. So for instance, in the spheres, if you have a sphere of odd dimension, the topological complexity is 1, because in order to move from one point to another point, you take the shortest path. You only have problems with the antipodal points, but then you use that in the sphere you have a vector field without singularities, which shows you the good path to come from one point to another. So you only need two open sets. But in the even spheres, you have a field which has one singularity. And so you must cover this situation, and you need a third open set. This is why the topological complexity of S2 is 2. Okay, so the general relationship is that the distance between two maps is less than or equal to the topological complexity of the codomain. And I wrote the proof here, and it's also very easy just by using the property of the composition. Okay. So I said that proofs are very easy in our setting. For instance, if you want to prove that the category is less than or equal to the topological complexity, you just write the definition, you write the constant map like this, and the identity like this, with the inclusions and the projections, and you use the inequality for the compositions, and the proof is done. And if you want to prove, for instance, that the topological complexity of X is bounded by the category of the product, you just take the definition, and this distance is less than or equal to the category of the domain. So it is a very good language to do easy proofs. We now study the behavior of the homotopic distance under products. This is a previous lemma. If you have two maps and you make the product with a third map H, then the distance between the products is the same as the distance between the original maps. And the proof is very easy. I wrote it here, but you can try. You only use these composition properties and the previous lemma, of course. No, sorry, just the compositions. The previous lemma is used in the general theorem, which is that if you have two maps Fg and another maps F'G', then the distance between the products is less than or equal to the sum of the distances between the factors. And for that, you just use the previous lemma and you use triangle inequality. So this is why this result is true, but you must assume that the product X times X prime is normal. So as particular cases, if you take the identity and a constant map, you obtain the similar result for the category of a product. And if you take the projections, you obtain the result for the topological complexity. And to end this first part, I will give a cohomological lower bound in terms of the length of the cap product, which is similar to those existing for the category and the topological complexity. If we have two maps F and G, and we take the induced maps in cohomology, then I call JFG the image of the morphism F star minus G star, and then the distance is bounded below by the length of the cap product. Okay, so now I will speak about applications to motion planning of the homotopic distance. You know that Lusternik-Schnirelmann category and topological complexity are of interest in robotics and in engineering because they measure the difficulty of planning motions in the configuration space of a mechanical system, which is equivalent to LS category and topological complexity can be seen as the Schwarz genus of some path vibration. And the same is true for the homotopic distance. If you have two maps and you consider the pullback of the path vibration by this map, which has components F and G, then the distance between F and G equals the Schwarz genus of the pullback vibration. That means the number of open sets in X such that there exists a continuous section on each open set. With this interpretation, we can see the homotopic distance between two maps as a solution for the following generalized motion planning problem. If you have an arbitrary point X in X, you must find a continuous path Sx joining Fx and Gx in Y in such a way that the path depends continuously on X. This applies to other invariants, which can be seen as particular cases of the homotopic distance. For instance, of course, LS category that we know, which is the solution to the following problem. You have a machine that must move from the current attitude X to its original attitude X0. You want to know the number of algorithms needed to determine a continuous path between them. And the solution is to find a homotopy between the identity and the constant map. This is the Lusternik-Schnirelmann category from this point of view. After you have the original interpretation of the topological complexity by Farber, you have a machine that must move from one position X to another position Y, and you need algorithms to determine a continuous path between them. The solution is to find a homotopy between the two projections. This is the original definition of topological complexity, but there are more invariants which are included in our setting. For instance, the naive topological complexity of the work map, which was studied by Farber, Murillo and Gu and Scott, and which is denoted by TCF. Here, X is the configuration space of a multi-arm robot, and Y is the workspace, that is the spatial region that can be attained by the end device of the arm. So you have a so-called work map, which assigns to each state of the configuration space the corresponding position of the end effector. So for instance, in the figure, you have a robot which has a configuration space which is a torus T3, but you have as spatial region R3. Another invariant is, so here you have the formal definition of naive topological complexity is the least integer n, such that you can cover the product by n+1 open subsets, such that on each UI there exists a continuous map which satisfies this formula that can be interpreted as you have a pair of points and you need a continuous path gamma joining fx, and I wrote here fgx, but this fx, okay? So it is clear that the distance between the projections composed with f is TCF. This is our result. And you also have the topological complexity of a vibration defined by Pavesic, which is the number of partial solutions to the motion planning problem, which sends each path into its origin X and the image of the final state. So you assign to each path the initial state X and the end effector position Fy. This is a figure taken from the paper by Pavesic, where you see what is called a triple roll wrist, and the configuration space is the torus T3, and the space Y is rotations. And finally, there is, so our result is that if you consider this vibration invariant, the complexity of F equals the distance between the projection, the first projection on X composed with F, and the second projection. And finally, there is an invariant called weak category by Yokoi, which is of interest when studying a notion of discrete Conley index. The definition is the weak category of F reduced to A is a subspace, is the smallest integer n, such that you can cover A by n+1 open sets, and its restriction of F power some k is null homotopic for some k. And we interpret that in terms of the distance, saying that the weak category is the limit of these distances from Fk to the constant map. And here I have introduced the notation for what we call the relative homotopic distance or subspace homotopic distance, which I shall explain now. So we propose the following definition of subspace or relative distance as a generalization of the usual definitions for subspace category and relative topological complexity. If you have two maps and a subspace A of the domain, the subspace distance is just the distance between the restrictions of F and G to A. We shall use this notation. Now I shall explain the relation between homotopic distance and Morse-Bott functions. So we study the relationship between homotopic distance and criticality. We know the famous Lusternik-Schnirelmann theory that you have at the end of the page, which says that the category of the manifold where it is defined as a differentiable function is bounded by the number of critical levels plus 1, which is less than the number of critical points. This is the most known version, but in fact, the following result, which is more elaborated, already appeared in the Lusternik-Schnirelmann original work. I heard it for the first time in a paper by Rudiak and Slenk. The theorem says that if you have a compact smooth manifold and you have phi, a smooth function with critical values C1, Cp, and you call sigma I the set of critical points in the level Ci, then the category of M is bounded by the sum of the subspace distances of the critical levels. So in particular, you have that it's bounded by the number of critical levels. And Farber proved a similar result, but for Morse-Bott functions. If you have a compact smooth manifold and phi a Morse-Bott function which satisfies these conditions that you have there, then the topological complexity of the manifold M is bounded by the sum of the relative topological complexities of the critical levels. And Farber called a function like that a navigation function. I shall explain later what that means. So let me recall what a Morse function is. You have a compact smooth manifold and a function phi is a Morse-Bott function if the critical set is a disjoint union of connected submanifolds sigma, and for each critical point, the Hessian is non-degenerate in the transverse directions. So for instance, there you have a height function on the torus. The critical manifolds are the horizontal parallels, and you see that the gradient is orthogonal to the critical manifolds. So this is a Morse-Bott function. Of course, Morse functions are particular cases. So if sigma is a critical submanifold, the basin of attraction or the stable manifold of sigma is the set of points such that if you take the flow passing through the flow ends in the critical point in sigma. So you have a point in the manifold, you follow the gradient and you arrive to the critical. This is the projection pi, which is known to be a fiber bundle with fiber R m minus n minus k, where m is the dimension of m, n is the dimension of sigma, and k is the index of sigma. That means the number of descending directions of the flow. And M is the disjoint union of the stable submanifolds. It is important to note that the global map, which sends its point to its, which sends its point to the final point of the flow, this map is not continuous. It is only continuous on the stable manifolds. Okay, so our main result is that if you have phi, a Morse-Bott function in the compact smooth manifold M, and C1, Cp are the critical values, and you call sigma I the set of critical points in the level Ci. And now if you have two continuous maps defined on the manifold, then the distance between F and G is bounded by the sum of the relative distances on the critical manifolds. So the two theorems before are particular cases. And for the proof, we follow the proof from Farber for the case of topological complexity. You consider the basing of attraction of a critical submanifold, and then the projection is a homotopy equivalence. So the distance on the critical manifold is the same as the distance on the basing of attraction. And now its stable submanifold is a submanifold. So it is an ENR, a Euclidean neighborhood retract. So you can find an open subset, an open neighbor, where the distance is the same as that on the manifold. And finally, since the manifold is the union of the stable submanifolds, you use the subadditivity of the distance and you find the result. Now I want to interpret the preceding results in terms of navigation functions that solve the generalized motion planning. It was noted by Farber that the negative gradient vector field of a Morse-Bott function gives rise to a flow which moves any initial condition towards a target critical point. Therefore, so-called navigation functions provide motion planning algorithms for moving from an arbitrary source to an arbitrary target. He gave an explicit description of motion planning algorithms based in a navigation function, and I shall adapt his explanation to our generalized setting. So assume that you have two continuous maps Fg defined on the manifold M, and that you have a Morse-Bott function phi on M. Then first you solve the problem in the critical levels. That means you find a decomposition of the critical submanifold into E and Rs, which solve the generalized motion problem. That means if you have a point in the critical submanifold in a certain piece, you are able to find a path between F alpha and G alpha. Here you have the maps F and G. Then you consider the basis of attraction of these pieces like this. And if you have a point here, you move the point through the gradient flow to arrive to the point, to the critical point, and you take the image of this path by the map F. And so you have the path from Fx to F gamma. There you have the path gamma you found in the critical manifold. And finally, you compose with the path, which is the image by G of the inverse path. And so you have solved the problem between Fx and Gx. So as I said before, this applies to all the invariants we saw were particular cases of the homotopic distance. Now I want to apply the precedent ideas to a new situation. We shall consider a submanifold N of a complete Riemannian manifold M, and the function phi given by the square of the distance from a point to the submanifold N. It is well known that this function is not differentiable in the cut locus of N. So let me recall the definition. You have a unitary geodesic starting in N, which is orthogonal. It is a minimizing geodesic until the point T0, but it is not minimizing after this point. So you say that this point is a cut point, and the cut locus of N is the set of all these cut points. For instance, if you have a sphere and you take as submanifold the North Pole, then the meridians are geodesics. They minimize distance until you arrive to the South Pole. This is a cut point. So cut N is the South Pole. If you have the projective space as a quotient of the sphere, then you have the point corresponding to the North Pole and the South Pole, which are identified. Sorry, South Pole. And now you take the geodesic, but the geodesic is minimizing only until the equator. So the cut point, the cut locus of the North Pole is the image of the equator, which is the projective space RPN minus 1, if your space is RPN. But in general, the cut locus is very difficult to compute. It is very, very wide. So an easy place is the torus. If you have the torus seen as a quotient of the square I times I, the usual Riemannian metric on R2, induces a Riemannian metric on M. And so if you see the geodesics starting at this point, the geodesics are the straight lines. So you see that this line is minimizing only until here, because it is this line and would be shorter to do this. Okay, so the cut locus is the image of the boundary of the square. And this can be written as the cut locus of this point is the cut locus of the first coordinate on S1 times S1 union S1 times the cut locus. And this formula is a general formula that will be true in many places. Okay, so we need this theorem from Basu and Prasad, which says that if you have a closed embedded submanifold of a complete Riemannian manifold M, and you have the distance function with respect to N, then the restriction of the function d squared to the complementary set of the cut locus is a Morse-Bott function, and the critical submanifold is N. So the gradient flow deforms M minus cut N to N. And so we are able to prove the following theorem. If you have a compact analytic manifold and N a closed analytic submanifold, and you have two continuous maps F and G on M, then the distance between F and G is bounded by the sum of the relative distances on the manifold and on the cut manifold. The cut locus, I want to say. The proof needs that the manifold be analytic, because in this case, it is known that the cut locus is a finite simplicial complex, so it is an Ian R. So you can find an open neighborhood U such that the distance on the cut locus is the same as the distance on U, the relative distance. And since M minus cut N is open, which is a theorem by Basu Prasad, then you have that M can be written as the union of these two open subsets, and by subadditivity, you have that the distance is bounded by the distance on the cut locus and the distance on N, because N and M minus cut N have the same homotopic type. A consequence of that is that the category of a manifold is bounded by the sum of the category of N and the category of the cut locus, which I think that it is a new result. And if we apply that for the topological complexity, then we obtain that the topological complexity of the manifold is bounded by the sum of the topological complexity of N times N and the topological complexity of the cut locus of n plus n in the product. And for instance, if the n is a point, then it is known that the cut locus of n times n satisfies a formula which is similar to what we said for the torus. But I don't know a general formula for any submanifold. What is important to notice is that what is not true is that the topological complexity of M is bounded by these topological complexities, because, for instance, if you take a sphere where the topological complexity is 2, as before, and you take the North Pole, the sum is 1. So the result is not true in this form. And as I said before, the general result is very difficult to compute in concrete examples. So I think this is all. You have here some references, the Basu Prasad paper I cited before, the paper where Farber spoke about navigation functions, our paper in Cambridge Journal, and another paper that we posted this week in the archive, and the papers by Murillo Gu, Pavesic, and Scott. And thank you very much. That's all. Thank you.
Okay, everyone, if you would unmute your microphones, you can all clap.
Thank you.
Thanks. Are there any questions for Kike? Anything?
Yes.
Yeah, who was that? Ask your question.
I can ask something if there's no one.
Yeah, sure, Mark, go ahead.
So I guess that you maybe thought about Lie groups as a source of examples where you might be able to understand the cut locus of some nice natural submanifolds and try and apply this to computing the LS category of some Lie groups. Have you thought about any examples like that?
Yes, of course. We are trying to do some computations because for the symmetric spaces, and in particular for the Lie groups, you can define the cut locus in terms of what is called the first conjugate locus, where you must compute the exponential transverse to the submanifold, and to watch the points where this exponential has a singular differential derivative. So it is not difficult to compute the cut locus, but the general results are from Lie theory and are complicated to understand in a concrete example. You see, there are some results using the adjoint representation, and in a concrete example, for instance, the unitary group, we prefer to do some explicit computations of the geodesics and to compute by hand. We are trying to do that, but at the moment, for the moment, we have no results, concrete results.
I guess one thing I was thinking of was that, so category of SPN is known for low values of n, and maybe like you could try and bootstrap up from the lower values by embedding them into higher values or something like that. That was.
Yes. In fact, Maria Jose Pereira and me published several years ago an upper bound for the category of the symplectic group, which used a Morse-Bott function. And so this kind of computations is similar, but we are trying to see if that gives something new. We are trying.
Any other questions?
I just want to say that it's a very interesting approach, and thank you for your talk. It looks very elegant and interesting. But what I wanted to ask is that, I mean, you showed that many notions can be expressed through this distance. What about this parameterized TC, and what about higher TC? Can you also express?
We didn't try. We didn't try. We tried to include some other invariants. For instance, there is a notion of relative category by Rudiak, and we know this parameterized topological complexity, but we didn't try all the possibilities, or we were not able to prove something, but we shall try.
Thanks.
Yeah, I would also like to know higher TC, whether we higher homotopic distance. That would be a good topic, I think. Anything else?